Hi, everyone. Today's guest is Professor Martin Kuldorff. Martin is a professor at Harvard Medical School. He has had an extremely enviable scientific career. His publications have garnered over 25,000 citations, and his biostatistical work that he has developed is part of the CDC's approved statistical methods for surveillance and risk surveillance. He is the co-author of the Great Barrington Declaration, and he works in spatio-temporal modeling, amongst many other things, which I find very interesting. Martin, welcome. Thanks so much for coming on. I appreciate it.
Thank you so much, Glenn. It's a great pleasure.
And so I guess, obviously, I suspect a lot of statisticians have heard of you and about you and probably from you at this point. And I am really glad that we can be one of the conversations that's giving a bit more of a statistical focus to the work that you've done. But maybe just to start off, we have you've worked in safety surveillance. You are an eminent professor and academic in the issue of safety surveillance, and you have developed biostatistical methods for safety surveillance. For example, spatio-temporal modeling, the multiple comparisons, types of adjustments that are required for sound scientific inference. And you've also said a number of interesting things like, these infectious disease outbreak models have applications in other fields as well. So that, for example, in oncology. So there's obviously a lot to unpack there. But maybe where should we start? I will leave it to you as the expert. I think it's interesting, the idea of using spatial-temporal modeling to model infectious diseases, because there are a great many of them. And also you've said that you try to minimize the number of assumptions that go into your statistical models. So maybe where should we start, do you think? What's a good approach?
Yeah, so there are different important statistical methods used for infectious diseases. But the one that I've been working a lot on is, as you say, spatio-temporal models. And the idea there is that when we have an infectious disease outbreak, and it doesn't have to be a pandemic, it could be a salmonella outbreak or a Legionnaire's disease or something else, it's important that we detect them as soon as possible. Because the sooner we detect them, the sooner we can find what's causing it, and then we can sort of remove the threat if it's, for example, salmonella in some food product that's been contaminated. So I've developed what's called space-time scan statistics. And a scan statistic is when you scan an area, either it could be time or geography or both. So you scan an area to see if there's a cluster of events. So it's the cluster detection method. So the idea is that if we have, for example, salmonella, that's a reportable disease. So every case of salmonella needs to be reported to the public health department. And then we can sort of continuously monitor when there is a new case of salmonella. And if there suddenly is an increase, let's say in Brooklyn, a neighborhood in Brooklyn, of salmonella, then we have to investigate what's causing these excess cases. And the key thing that the statistics can do is to detect this as quickly as possible if we sort of run the analysis on a daily basis, then to detect as quickly as possible. And one example is, I think it's 4 or 5 years ago now, there was a huge outbreak of Legionnaire's disease in Bronx. It's the second biggest Legionnaire's disease outbreak that ever occurred. And that was detected by the New York City Health Department using these methods of space-time scan statistics that I've been developing, and I work closely with them. So because of that, these disease outbreaks of Legionnaire's disease could be detected a few days earlier than it otherwise would have been. It would have been detected no matter what, but even 2 or 3 days earlier makes a big difference in terms of finding what caused this outbreak. It turned out it was a cooling tower at the top of a building that had been infected, and that was spreading it in the neighborhood. So as soon as that was found, of course, that cooling tower was sort of removed or cleaned so that it wouldn't spread it anymore. So that's very important. The other thing these methods can be used for is once there is an outbreak, they can be used to monitor the outbreak. Where is the outbreak increasing? Where is it decreasing? And so on. And so this method has been used during the pandemic to monitor the COVID when there are new areas that are affected, etc.
Cool. And so I guess when I think about disease outbreaks, especially at the onset of an outbreak, essentially what we're having are the data points are, these single instances. It's a number of individual data points. And spatio-temporally, you're talking about that the patients will either have, it'll be sort of essentially like a dot process. Is that
sort of a point process? Yeah.
Yeah. And so we have this point process, and then essentially in this point process, we'll presumably have some correlation in the spatial, in some spatial features, and then also temporally it'll have some correlation. And the idea would be that if there are, and then of course there are probably other socioeconomic features as well that you might want to include. So what are the types of features that you would include beyond space and time to detect anomaly?
So age is often important to adjust for because many diseases are age dependent.
Mm-hmm.
So that's one thing that we often include, but we may include other things also to adjust for depending on the disease. And it's not only used for infectious disease; it's also used for cancer or other things. So it depends on the disease. In terms of correlation, I think in spatial statistics, there's sort of two things that are interesting. Sometimes we want to study a particular hypothesis, like is the exposure to radon, for example, does that influence the risk of some form of cancer? So then we have geographical measurements of the cancers as well as the exposure. And when we do that, we often have to adjust for any spatial autocorrelation because to get proper inference, because there could be other factors that we are not adjusting for that is spatially correlated, and we want to adjust for that to get proper inference. But when we do detection and monitoring, we're actually looking for those correlations.
Mm-hmm.
So we are trying to look for areas where there is spatial correlation because there's a cluster of cases. So therefore, when we do the outbreak detection, we can't adjust away all that correlation because that's actually what we want to detect. So therefore, it's sort of a different setting where you do more causal inference. You're trying to find out if this exposure causes this disease with spatial data, versus in a surveillance setting where you're trying to find out where is there a new outbreak occurring. And obviously, you don't want to sort of treat every random chance occurrences as a new outbreak because if you start investigate them, you don't want to investigate cases that are not related. But in surveillance, it's not so key necessarily to find out if something is statistically significant or not. It's more a question of which ones are the worthwhile doing an investigation for. So even if something is not statistically significant, you might still want to investigate it sometimes, and you could still maybe find that 3 cases were not enough for statistical significance, but they got the disease from eating the same cheese, for example, bought in the same store or whatever.
Because I guess for example, the Legionnaires in the Bronx example, presumably you weren't, manually scanning for that location and disease combination at that time, or perhaps you were. But are these models essentially, are they automated in some way such that they are meant to flag anomalies in advance, and then that would instigate a manual inspection, or how do these things actually work in practice?
Yeah, so they are automated with daily analysis. So the new cases are reported to the health department every day, and then usually they run it overnight, and in the morning they'll find out is there something that is flagged.
Mm-hmm.
It does use different diseases. So it does one analysis for each disease, for Salmonella, Legionnaire's disease, and so on. But there's no assumptions about the location or the size. So the space-time scarcity is uses a cylinder with the base, the circular base, could be very, very small in size. So it's only one zip code, for example. Or it could be very large, encompassing all of Brooklyn.
Mm-hmm.
At the same time, the height of the cylinder is time. So it could say, okay, there's an increase in the last 2 days. Or it might be sort of a more slowly emergent thing, so that we look for 4 weeks. That has sort of been a small but gradual increase in cases for a 4-week period. So we don't want to assume where or the geographical size or the temporal size. So that's very flexible in this detection system, surveillance system. And then then we adjust for the fact that we're looking at so many different areas and so many different time periods. So we adjust for that multiple testing to see, and then we can sort of say that, well, we put a threshold so that if there's nothing going on for disease, we will get 1 false alarm per year, for example, or 1 false alarm every half year, whichever we prefer. And then when something is flagged, let's say there's a salmonella thing flagged in Brooklyn, then the health department will investigate. And this is not research, so health department has the right to talk to these people and ask, okay, you have salmonella. Where did you go shopping the last week? What have you eaten? Did you eat peanut butter? Did you eat fish? Did you eat some cheeses? Where did you buy it? And so on. And then they can see, if they interview 10 people, they can see is there a common denominator that they all ate the same brand peanut butter bought in the same store, for example. Of course, in the Legionnaires' disease, it wasn't food, so they looked at different things, and they did expect cooling towers as one of the options, and they did testing and multiple cooling towers. And eventually they found that most of them were fine, but there was one that was contaminated with Legionnaires' disease.
Do you have a pre-specified set of diseases that you're particularly looking for? So, for example, salmonella seems like one that really pops off the top of your head about something that you'd be scanning for, because effectively we have a food supply chain, and but for other diseases, is there a common set, or is it that you don't even need to relegate yourself to a set because you have a sufficient computational capacity to search?
No, it's usually a common set, and that depends on the health department and so on. So, for example, New York City monitor, I think, about a dozen different reportable diseases. And I forget exactly what's on the list, but it's those things that... So you wouldn't monitor, for example, ear infections.
Mm-hmm.
It's very common, and it's not a reportable disease. You could still do it through electronic health records, but it's not typically to do that. But salmonella is important because it's often foodborne. So you can actually do something if you find something. You wouldn't. So another one you would not look at would be anthrax, because that's so rare.
Mm-hmm.
And if you have one case of anthrax, they will be investigated immediately. So one case of salmonella, you wouldn't necessarily investigate, but one case of anthrax, you would certainly investigate it wherever it occurs, whenever it occurs. It's such a serious thing.
Yeah, so no statistical model, for example, would be needed for that, because essentially the data point is sufficient in itself to generate all possible medical intervention.
Yeah. So you don't need statistics, because as soon as there's one case, the health department will go there and try to find out what's going on.
Yeah, I do like examples like that where, because obviously, when we're in our technical fields, we really do enjoy creating methods and tuning these methods so that we have this really great data-driven approach to something that's important. But then at the same time, there are plenty of instances where effectively you don't need a sophisticated methodology. The only thing you need is actually the data is the signal in itself. And so obviously there are certain medical outcomes and diseases that would have that. As you mentioned, anthrax, I assume that bubonic plague might be another one like that.
Ebola also, I think.
Ebola, yeah. And so if you have those, obviously you don't need sophisticated statistical methodology to say, oh, let's adjust for multiple comparisons, because after all, we were looking for these other diseases too. These ones you have enough, but for these other diseases like salmonella, trying to say, is this a one-off that one person might have gotten, or is it sufficiently correlated in time and in location, such that we actually realize that there's an exposure to it?
Yeah, and that's why also it's so fun and interesting to work with public health agencies, public health officials, because they know the public health aspects of things. So you have to sort of try to combine what are the public health needs that they have in a particular jurisdiction with what can the statistics do and cannot do.
If you don't mind me asking, is your work essentially, are you applying these models in different silos to different public health authorities? So, for example, like perhaps each New York borough you might be reporting to, and you deploying them to those, and then there's the greater city of New York, and there's multiple cities? Or is this more of you scan on the national level and then you send the relevant information to local authorities?
Most of it is done more locally. Not so in New York City, for example, is the New York City Health Department, and that seems local for a city. But I mean, the city has 8 or 9 million people, so it's of course a huge area. But otherwise, it could be the Illinois State Health Department who does it for Illinois, and Indiana State Health Department does it for Indiana. It has been used on a national level also, but maybe more retrospectively, not so much prospectively for the early detection, because it's really the state health departments typically that are responsible for this kind of surveillance. And the same in Canada, for example. So the Quebec Public Health Department is using it for Quebec and so on.
Do the models need a large amount of, for example, hand tuning or adjustment as they're being applied to these different locations? So essentially, like, is there a team of grad students and postdocs and professors who essentially each time some of the surveillance, these surveillance algorithms or the models are being applied to a new location, is there a lot of essentially activity, or is it just essentially you hook it up and you make sure that it works within the current data framework and then see what happens?
So it's usually done by the health department staff, and they have to. They have to do it with their data, and then they have to sort of define the geography of the area. So what are the latitudes and longitudes for the census tracts or census block group or zip codes, whatever they're using for their particular state or city. But that's sort of the main part of the customization. And then the rest is often fairly standard. And there is the software there's a free software called StatScan that can be downloaded from statscan.org. So SAT scan stands for Space and Time Scan Statistic. So health departments download that software and then they can run the analysis, and it's fairly straightforward for them. So it's not too complicated, I think.
Cool.
And the method and software are used by, I think, almost all the state health departments in the US, and of course by CDC and many health agencies around the world. Yeah, for different diseases. So some might use it more for infectious diseases, others might use it more for cancer, for example.
Yeah, I definitely want to hit on the cancer bit in a second, but before we do, I was interested in the multiple comparisons aspect, just to double back on some of the specifics. Is it essentially because you have multiple time periods over which you can scan? Presumably, you also might have multiple localities, or I guess spatial elements. What are sort of the different features by which you are adjusting for multiple comparison? And I guess one of the other questions is, what is your intuition about how to do that, given that effectively a lot of these outcomes are correlated? So essentially, the hypothesis for which you're adjusting, you're not just testing a large number of independent hypotheses. You are effectively testing. I assume that you're testing these things and they're fairly correlated, or at least correlated in some level that might not be clear.
So the multiple testing is taken care of with scan statistics, and that was something that was invented in the 1960s by Professor Joe Naus at Rutgers University. And in the simplest version, it's just the time. Mm-hmm. So you have a timeline, and then you have observations in time, and then you see, are there any clusters, or if this just comes from a uniform distribution. And you condition on the total number of observations seen. So you're not interested in how many observations there are, you're interested in how they are distributed over time. So what the scan statistics does in time is it sort of drags a window along this timeline, and then it sees where are there is there a cluster, and then it evaluates the probability of that. That would happen anywhere along the timeline. So what happens is that if it's truly uniform, then you only have a 0.05% risk of rejecting the null for any place on the timeline or when the space of geography. So if it's truly are no clusters in the data set, then 95% of the time we will not reject the null hypothesis. Mm-hmm. And 5% we will erroneously reject the null hypothesis for some location there. So that's how we sort of adjust for the multiple testing. So it's not a Bonferroni type adjustments, which is sort of most common one. But they don't work in a scan statistic because these intervals are so dependent, and these circles, because we look at this circle and then this other circle, which is almost the same, but just a little bit off. So there will be thousands and thousands of circles all overlapping. So therefore, a Bonferroni type adjustment would be far too conservative. And that's what we use instead, a scan statistic, which is sort of another way to do multiple adjustment for the multiple testing of many overlapping intervals and circles.
Yeah, that was what was popping in my mind, because I had assumed that you weren't doing something was it fair to say ham-fisted as a Bonferroni adjustment, because effectively when you're looking at these time periods, a test on Monday versus Monday plus 1 hour of Tuesday, those aren't independent. And so to essentially be doubling your possible airspace is not realistic. It's a marginal increase on top of that.
Exactly. That's exactly why the Bonferroni type adjustments does not work in these settings.
Can you use any, does any sort of like biological or mechanistic knowledge make its way into these adjustments? So effectively, given what you know about certain diseases and, for example, their incubation time or the amount of time that it takes for them to wear off or recovery periods, does any of that information actually work itself in, or is that too complex?
No, that's a very good question, and the answer is yes, it does. So depending on the disease, for example, the maximum temporal length of the outbreaks that you're looking at could vary depending on what disease it is. Mm-hmm. Sometimes it might be enough to have a week only. Sometimes you might have a few months, mm-hmm. depending on what type of disease it is. The other thing that comes in is in the geography. I mean, the easiest is just to have the latitude and longitude for each, let's say, census tract. Mm-hmm. And then you see which ones, you have one latitude and longitude for the center of each census tract, and then you see which ones are close and which ones are not close to each other. But if you want to be a little bit more sophisticated, you can take into account the geography more closely, because maybe two places are very close, but there's water in between. Mm-hmm. So there's actually not very much communication. You have to sort of maybe it's the river. You have to drive up 20 miles up the river and over the bridge and then back. Mm-hmm. So in effect, they are, so geographically they are very close to each other, just across the river, but in practice they are not, in terms of where people go shopping, for example, and so on.
Yeah.
But that also depends a little bit on what is the what is the source of the potential outbreak. If it's, for example, salmonella, we were looking for more foodborne things, maybe they shouldn't be close. On the other hand, if it's Legionnaires' disease in a cooling tower, well, that can, even if the cooling tower is on one side of the river, that can sort of, if the wind is in the right direction, it can go into the other side. Mm-hmm. So sometimes you may want to do that and sometimes not, depending on the disease and the geography.
Yeah, I guess because one of the sort of an imminent example that comes to my mind about how geography might essentially, I view it as like a sort of a geographical length scale. So how quickly that these sort of events decorrelate over a small distance versus a large distance. And you think about something, for example, that is transmissible, and you have a transmissible disease, but it happens in an affluent neighborhood, for example, such that the people don't need to go outside, or that the people don't need, they can essentially stay at home and remain essentially segregated from the rest of the community. And in contrast, you might have a working class neighborhood such that the person does not have that benefit. And then they can effectively, someone with a communicable illness or an infectious illness within that working class community, effectively, not having the luxury to just stay home means that they do have to go out, and that there is effectively more of an exposure. There's more of an area of exposure or an exposure trail for those types of patients.
That's true. And I mean, COVID is a very good example for that, because those of us who are in the professional class, like scientists or journalists or attorneys, etc., have often been able to work at home, even younger people who are extremely low risk from COVID, while working class people have, they must work to make a living, so they have been out and about much more. And we also see that in the statistics for COVID, that, for example, from Toronto or Los Angeles, in the very beginning, a little over a year ago, it was fairly even in the more or less affluent neighborhoods. But then when the lockdown was put in, it continued to go up in the working class neighborhoods, while the more affluent neighborhoods was held down. So the lockdowns was sort of a shift of the burden of the disease from shifting the burden from the more affluent to the less affluent.
Mm-hmm. Yeah, it also reminded me, there's a recent study, I believe, that was looking at cell phone data, and it looked at the mobility of just the general population due to cell phone data. And it was very clear that effectively people with white-collar jobs had the ability to stay essentially immobile. They moved around less, whereas people who have to work blue-collar jobs, in-person, physical jobs, you can't hide behind your computer screen, that those people essentially still had to keep moving and circulating throughout the population.
Yeah. And that was the sort of the basic idea behind the Great Barrington Declaration that I wrote with two other infectious disease technologists, Professor Sunita Gupta at Oxford University and Professor Jay Bhattacharya at Stanford Medical School, that instead of protecting the affluent, what we should do, since everybody can get COVID, but there's more than 1,000-fold difference in the mortality risk between the oldest and the youngest. So the best way to minimize mortality would be to protect the older people, whether they are affluent or working class. Mm-hmm. We failed to protect the older people, especially the working class older people. So instead of protecting the affluent, we should have focused on protecting the older people, while letting younger people sort of continue with near normal activities, to sort of keep society running, so that we didn't get all these collateral damage on public health, like missed cancer screenings or cancer treatment that has sort of gone undetected, mm-hmm. or worse, cardiovascular disease outcomes that we've had, plummeting immunization rates for children, and of course, worse diabetic treatments, and of course, a mental health situation that has deteriorated a lot during this year.
Yeah, I've definitely seen. I've seen, for example, that I believe that cancer diagnosis rates in, I believe, multiple countries. I've only looked at a few countries that I'm sort of more familiar with their healthcare systems, but that, for example, cancer diagnosis rates have dropped precipitously, and obviously, the cells are still splitting. The underlying mechanism has not changed. The amount that keeping people inside away from the sun is not the only reason why these cancer rates are dropping. It's because effectively there's a there's a lower detection threshold, and or I guess an increased detection threshold where people aren't being detected, and obviously that's there's, I guess, a competing risk aspect to that, but at the same time, with our aging population, we do have these immense burdens for people as they increase the risk of cancer, and you do have to be weighing that out. And for example, fewer young people have cancer, but if you are diverting your attention to one specific ailment, you're missing out on the holistic public health aspect.
Exactly, and that sort of goes against the basic principles of public health, that you have to look at public health as a whole. So, I mean, so the number of reported cancer has gone down, and it would have been great if that was due to less cancer, but obviously it's not. It's just that they're not getting detected, as you're saying. So, but it doesn't have immediate impact on mortality, because usually it takes time from detection until you have mortality. But let's say a woman who might now die from cervical cancer, like say 3 or 4 years from now, instead of living another 15, 20 years.
Mm-hmm.
So these consequences of the lockdowns on public health is something that we're going to have to live with and die with for many years to come, unfortunately.
Yeah. And I guess one of the other bits on the sort of the time scale issue is that effectively the detrimental aspects of these decisions have meant that you can't even measure them, because it is a bit, there's an estimate how many people are going to die of cancer in 5 years, how many people because of a mistreatment or something like that. So effectively, data still needs to be collected, and I guess you still do have estimates of you can look at these long running cancer diagnosis trends. You look at the difference between what the long running trends are and how many people were diagnosed last year, and effectively that means that you have this many free agents out there who you now need to go back and retrospectively try to track down. Essentially, if you have 2 million cases on average, and last year you only identified 500,000, that means you might have 1.5 million people out there who now you need to go and identify and find out, okay, who has cancer that we missed, and now it's at a later stage.
Yes. So we will eventually, I think, know how many extra deaths we will have from cancer, and how many life years were lost. But you're right, it's sort of not easy to know that now, even if we know how many undiagnosed cancers there have been. So you're very right about that.
One other bit that I find curious is obviously, we live on a planet, and that planet has 2 hemispheres, and therefore that there are, for example, seasonal differences between different locations. And it seemed a bit of an odd thing at the beginning to be comparing a large number of countries across both hemispheres, across a large number of geographical locations, and making inference on what tactics were effective at slowing down COVID. Because effectively, this isn't a scientific lab experiment where you can repeat it 1,000 times under a large number of confounding factors. And the issue of essentially, especially, for example, people in the media making comparisons between 2 countries' success rates, marginally into a pandemic, when 2 different countries might be on opposite hemispheres of the world, and therefore there's essentially this massive, there's a massive shift. And so essentially, depending on when the pandemic hit a specific country, you might either be protected or not protected. And so essentially, there's again another thing where there's a shift in whether or not you're actually assess the efficacy of an intervention.
Yeah, so the seasonal patterns is very clear for COVID, and so we can see that from the southern and northern hemisphere. And I mean, the pandemic started, I guess the first cases were probably around November 2019. So those countries in the northern hemisphere were very susceptible to this pandemic early on. And therefore it came into the countries before we could do much about it. It was already widespread, and then it's too late to do, for example, to close your borders and put the country in quarantine. So in a way, the smartest strategy is to put your own country in the southern hemisphere, because then you have actually the option of closing down the country, like New Zealand did, for example. They had a few cases there, but they could easily stamp those out because it was their summer. And then they closed their border with a 15-day quarantine. And they still had, of course, cases as Australia as well. So you can't seal the borders completely. But they were able, by doing that, to sort of keep the numbers low. And now if they vaccinate everybody quickly, I think they will be quite well off. But that was never an option that was available to the United States or any other country in the northern hemisphere.
Mm-hmm. What about equatorial countries? Because one of the things that strikes me about a place like New Zealand is that not only is it on the southern hemisphere, but it's actually fairly southerly in the southern hemisphere. So effectively, it will have more extreme cold conditions when its winter does arrive. I'm pretty sure you can take, or previously you could actually take commercial flights to go fly over in Antarctica from New Zealand. So essentially you could go look at the Arctic penguins or whatever, or the ice sheets in Antarctica in just a normal commercial flight. And so there's a difference between a country in the southern hemisphere that's just mildly below the equator versus substantially below the equator. Is there any information that you've had about what's happening in these sort of equatorial regions?
So they might have a very different seasonal pattern, but the thing is also we don't know exactly what's driving the seasonality. Is it the temperature? Is it humidity? Is it sunlight? Or other things? Mm-hmm. So there is something, but we don't know yet exactly what's driving it. So if we look at a country like India, for example, which is closer to the equator, then we don't necessarily know what is driving the seasonality there. Mm-hmm. But India also has a seasonal pattern, so that's clear, but we don't know exactly what it is that's driving the seasonal patterns, and hopefully we'll find out eventually.
Mm-hmm. Yeah, that's interesting. So what was the next thing I want to talk about? So if you don't mind me just sort of hopping around subjects, because one thing I didn't want to miss out on, because this sounded really interesting, was this sort of safety surveillance that you're doing for infectious diseases. And you said that this also applies to things like cancer. So how do you essentially bridge that gap? Because I guess there's maybe I guess usually when I think of cancer, I think of it as essentially a base rate that human beings have as a species, and then there are different sort of exposure factors on top of that would mean that people would have essentially heightened risk in certain areas. And obviously, there are some genetic predispositions for these things, but how do you bridge the gap from something like Legionnaire's disease or salmonella to cancer clustering and things like that?
So one difference is that in cancer, we're not necessarily so interested in new outbreaks. Mm-hmm. The bigger interest there is to understand the geographical patterns of cancer, to see if there are any areas with higher risk than other areas, and then try to figure out why. But also there are situations where the population are concerned about a potential cancer cluster because they talk to the neighbors or somebody working in the same place, and they find out that there were several cancers of some type in the same neighborhood. Mm-hmm. But of course, that's going to happen by chance. If you do a random point process, mm-hmm. you will have our eyes are very good, so we will be able to pick up some clusters even in random data. All statisticians know that, but not everybody in the public. So then the key thing there is to see, okay, there is a cancer cluster. Let's say there's a leukemia cluster somewhere in New Jersey. Another question is, well, is it really a true cluster that's due to something common risk factor, or is it just like a chance occurrence because there will be cluster somewhere? And we can't just draw a circle around the cluster and then compare that with the rest, because we call that the Texas sharpshooter effect.
Mm-hmm.
The Texan who first shoots his gun with a hole in the barn door, and then he draws the bullet,
target,
the target around that hole, and of course he always hit in the bullseye because of that. So that's sort of similar in cancer clusters. We can't just draw the circle around that town in New Jersey that there was a concern about a cancer cluster. So instead we have to look, let's say, at all of New Jersey, and then we can do the scan statistic. Now a purely spatial one without time, let's say from data from the last 10 years or so. And then we can run an analysis for leukemia in New Jersey and see, are there any clusters there? And if so, are they in that location that was suspected? And if so, is this likely a chance occurrence or truly due to something? So these statistical methods can be used to detect any cancer clusters, but equally important, it can be used to sort of determine whether those reported cancer clusters may just be due to chance. And my experience is that small cancer clusters that are reported in the media are most often chance occurrences, because clusters will occur somewhere just by chance.
Yeah. I guess my only correction on that is that the reporting of it is not a chance occurrence, because of course it makes for an excellent headline. So while the disease cluster itself might be a chance occurrence, the fact that the media will report on it as something to garner some attention is not a random chance.
I think you're correct on that one. So yes.
Does something like so I guess maybe for people who aren't as familiar with cancer, or various cancers, obviously tumors themselves can be heterogeneous. So effectively you can have a cancer tumor that is comprised of essentially, multiple strands. I'm not sure species isn't the right word, but essentially multiple distinct cell populations within that tumor. Can you use any information about the exact nature of which SNP mutations, for example, are available? If multiple humans were, for example, exposed to something that would cause cancer, would their mutations tend to be in the same way? So would a cancerous patient mutate in the same way, or do they all maybe mutate in different ways, but it leads to the same effect?
I don't know if we know a lot about that. Mm-hmm. Within cancers like leukemia, there are different types of leukemia.
Mm-hmm.
But in many cases, we don't even know what's causing many cancers. Obviously, we know with lung cancer, it's caused by smoking, most of it, and we know other things as well. But if you look at, for example, leukemia or brain cancer, we know very little about what's causing these cancers. So then it's also hard to know what causes specific types of cancers. But one could look at geographically and see, instead of seeing if the excess of let's say leukemia, we can check to see, are there any places which has more of the AML leukemia versus the ALL leukemias, so that the proportion of one particular type is higher than the other, and then adjusting for sort of the general distribution of leukemia. Another thing that we sometimes do is to look at the stage of cancer as they are detected. So, for example, breast cancer can be detected very early on or very late. And it's, of course, better to detect it early, because then we can initiate treatment sooner. And that's why we do mammography screening, to be able to detect it as early as possible. But we can then look at geographically to see if are there some area where the breast cancers are detected at a later stage. So we compare late and early stage. So is there a high proportion of late stage compared to the early stage? And that can then indicate for public health departments where there is a weakness or a lack of mammography screening, and where that has to be done better and reaching that population better. So that's another way to use this for very practical purposes in terms of providing good healthcare and where there are gaps in the healthcare system.
On the issue of late screening, is there any research in going back and sort of correcting the retrospective record based on what we found in later screening? So say, for example, do you find a stage 4 cancer patient? And you have essentially, so you have cancer data. Let's just keep things simple for 1, 2, 3, 4, 5 years back. And when you have these late stage cancer patients, effectively that does tell you, you don't just wind up with stage 4 cancer one day. There was a development period that was missed out on. And is there any work in sort of adjusting what might be that latent variable of underlying cancer based on the data that we have that we receive in the future?
Do you mean to try to find out when I sort of went from stage 1 to stage 2 and to 3 and 4, like the timing of that? I don't think I quite understood what you asked.
So the idea is that you can identify what the cancer rate of a population is by looking at when they're diagnosed. So you might have like a phase 1 cancer data for 4 years ago. But then as you get a stage 4 patient who previously didn't have any medical record of cancer, is anything done to adjust the stage 1 rates of years ago because that they had to have gone through that stage at some point?
Oh, I think I understand your question better now. So one issue is, for example, if cancer screening suddenly goes up,
mm-hmm.
if we do more cancer screening, then we will find more cases than we otherwise would have.
Mm-hmm.
So we might get an increase in cancer, but it's not due to more cancer. It's really due to earlier detection. So it'll be like a shift. And therefore, what looks like an increase in cancers is really not an increase in cancer. It's just that we're detecting it earlier, which will then maybe later on that effect will eventually go away when it's sort of a steady state for the detections. But there has been work done by, for example, Rocky Foyer at the National Cancer Institute and his colleagues to look at understanding whether these increases are due to actual increases in cancer incidence or if they are artifacts of changes in screening practices.
Mm-hmm.
And that's something that we're going to have to do now during the pandemic also. When screening went down, we had to sort of try to understand how changes in cancers were affected by differences in screening versus if there were anything that led to more or less cancer overall.
Yeah. Also, I guess another thing is I'm trying to decide between two things. One, I wouldn't mind asking a bit more about how certain people are about these basal disease rates. Cancer is one, but salmonella, any of these baseline diseases, even something as set in stone as, for example, mortality, where how well do we actually know what the baseline rates of these incidences are? That'd be something I'd like to discuss. But also the changes in instrumentation over time. Effectively, how can you adjust one screening method versus another? Obviously, you could the sort of like bland Altman agreement type stuff comes to mind, but the other issues like if you have two screening methods and you're replacing method A with method B, do people need to essentially adjust, or what adjustments do they do to make sure that the data is cohesive over time over different locations? Or is that just a little bit too complicated and people sort of hope to uniformly switch out the screening process over time?
No, I think you have to take that into account when you monitor cancer rates over time. And there's some very nice, I haven't done those kind of work myself, but there's some very nice modeling that's been done by various research groups
mm-hmm.
to understand cancer rates over time in terms of how it is affected by screening, or if you look at mortality, it's also affected by mortality rates. Changes in mortality rates are affected by both by screening as well as by changes in treatments. So I think it's very important to do that. And those are very interesting, challenging epidemiological and statistical problems that are fun to work on, I think. And a lot of people have done some good work on that.
Mm-hmm. Yeah, because I know just from some of my own research where it's always interesting, for example, when a patient is being monitored via one, they call it probe or mode of acquisition, one vital sign monitoring device, and they actually switch or they have an ancillary device as well. And you can essentially see these two different devices or even more, or even multiple channels from the same device, all trying to measure the same thing. And the idea is that if you are going to be creating a monitoring or surveillance system based on the data from those, it's heavily dependent on which device you're using.
Yeah.
And so, yeah, they definitely would not want to be. Go on.
Yeah, I agree with that. And at the same time, I think cancer is probably easier than many other diseases because we have usually good cancer registries.
Mm-hmm.
So, for example, influenza is harder because we don't test everybody for influenza. We would test very few people if they actually have influenza. So there you also have to have interesting models to monitor how influenza. And some years we have more influenza, and other years we have less influenza. But that also requires some interesting statistical models to model that. And there is more uncertainty because most cancers are detected and reported.
Mm-hmm.
But in influenza, only very small, very few of them are actually confirmed to be influenza, reported as such.
What diseases, because that's a useful thing, essentially the proportion of the disease population who you actually capture and get data on. What are the good sort of like dividing lines between those diseases? Something like cancer, it seems, obviously it's good to hear that most of those are caught. So we have a fairly complete idea about what the cancer population looks like. Influenza, sort of these common infectious diseases, on the other hand, obviously we aren't collecting cold data person by person. So are there any sort of like dividing lines or mechanistic lines by which you can capture most of the population of certain diseases and you don't capture most of the population of others?
I think one dividing line is whether there exists a registry or not. Mm-hmm. And most places have cancer registries. Another birth defects, we also have very good information on because we have birth defect registries. And of course, that's very important to have that. So diseases for which we have registries, we have much more information on. For other diseases, we have to rely often on electronic health records or insurance claims data.
Mm-hmm.
And they can be very useful for other diseases, but they don't usually have the same quality as a registry because they are false positives and false negatives and so on to a larger extent than with a registry.
And on that more general question, how much is medical coding of use for these types of things? Because effectively, there's more to medical. If you know the answer, obviously, there's more to medical coding than just simply recording data, and so there's more motivations than simply saying we're trying to create this objective view about what types of diseases and what types of treatments people require. Because obviously, there's an economic incentive to various types of coding. Are those types of data actually used in the academic research as reliable, useful data, or is it a little bit? Are they taking with a grain of salt, or are people sort of just trying to sort through and find out what actually corresponds to reality and what doesn't?
So we use those electronic health records and insurance claims data a lot in research. And they are very, very useful and very important data sets to use. And they will contain information from many, many millions, tens of millions of patients. And one area, for example, which I've been involved in, which are very useful, is to evaluate side effects of drugs and vaccines. Mm-hmm. Because when a drug or vaccine is approved, maybe it has been tested on 1,000 people, or in best cases, a few thousand. So we know about common adverse reactions, and if it's approved, those common reactions were all mild. But there could be more rare adverse reactions, serious adverse reactions.
Mm-hmm.
Or it could be that there are adverse reactions in certain groups that were not part of the clinical trials, like older people or children or pregnant women in terms of birth defects and so on. So these data sets are enormously useful for looking at that. And that's one thing we do. I've been very closely involved with the CDC Vaccine Safety Data Link to develop methods for monitoring the safety of vaccines, both data mining methods, where we don't have any, like just looking for any type of adverse reaction, as well as sequential analysis methods, where we try to detect any potential adverse reaction as soon as possible. And it's important for two reasons. One is because if there's a problem, then we want to detect it and we want to detect it as soon as possible. If there's not a problem, then we want to be able to say we don't have a problem, and therefore it's safe to take this drug for pregnant women, or it's safe to take this vaccine for older people, and so on.
In sort of for these topics, where essentially you're trying to, when you're exposing a new population to a treatment, or essentially not necessarily new, but you're expanding the N of the number of people under consideration, and you're trying to see, because it's very intuitive how this sort of same the intuition behind this statistically is, we have this basal rate of these adverse events in a population, and then we're trying to compare it to a specific subset of the population, which has been either exposed to this treatment or exposed to some, cooling towers or something like that, and making the comparison and saying, okay, does this patient population actually, are they experiencing a higher rate of risk? And then I guess on top of that, there's the issue of, given what they are, given this high rate of risk, for example, from a treatment, are they, does that actually outweigh all the other risks in the world that they have to deal with? So, for example, the idea is you get vaccinated, and it obviously reduces one risk, but it could expose you to other risks as well. For example, an allergic reaction to the vaccine, which I assume is something that a lot of people don't know whether or not they're allergic to any given vaccine, or even heard that they might have an allergic reaction. So essentially, people are trying to weigh out these different risks. A similar one might be, for example, staying inside and never leaving your house for, 18 months. And, there's a risk to that. There's also, you won't get hit by a car, but at the same time, if you're being sedentary, there's a cardiovascular risk to that. There's a psychological risk, unless you're a data scientist and you already work in front of a computer, 18 hours a day anyway. But how do you sort of weigh through those things? And are there some that get a higher priority than others?
Yeah, it's good to be outside in the sun.
Mm-hmm.
We need sunlight is good with vitamin D, and good to exercise. So it's always good to be outside for your health. So that's something I think we can all agree on. But I guess it depends on the disease. So, for example, if we have a drug for cancer, and it's a terminal cancer, and a drug can extend your life by a few years, then most people are willing to take side effects. And we know that many cancer drugs that have side effects, but we accept that. Mm-hmm. Because it is doing something good to us in extending life. So there we have quite a high tolerance, I think, for adverse reactions. Mm-hmm. Same thing with the COVID vaccine. If somebody is in the 70s, if they get infected, they have it's not a huge risk, but they have certainly a considerable risk of dying from the COVID. So there's a huge benefit of the vaccine. So even if there's a small risk, that's a risk worth taking, mm-hmm. Without any doubt. And every old person should get the vaccine to reduce the risk. So that's so that's very clear for older people. But then for younger people, because it takes when a new drug or vaccine comes on the market, it takes a couple of years before we know about the adverse reactions. Mm-hmm. So, for example, if you're going to buy a new car, I suggest you buy the latest model, because it usually has the fanciest features and so on. But if you're taking a drug, unless there's no alternative, it's usually better to take a drug that's been on the market for a few years, because then we know about the adverse reactions. We don't know that about the new drugs. So new drugs, if it's a unique thing that we don't have any alternatives, then we take it. But other than that, it's often better to take an older drug. So, for example, for younger people for the COVID vaccine, we know there are certain adverse reactions, but also the risk of mortality is very low for younger people. So we still don't know the full spectrum of adverse reactions to the COVID vaccine since it's so recent. So there's not clear what the benefit risk calculations are. So in such situations, I think people have to decide on their own whether they want it. And for example, we shouldn't have mandates for vaccines in such situations where they are still unclear what the benefit risk ratio is, since we by default cannot know that until a few years after the vaccine has been in use.
Yeah, it is an interesting aspect that effectively there is long-term surveillance. It's been well established that long-term surveillance is necessary to essentially, there's a reason that they're called rare adverse events, because they are rare. And these rare events, if you miss one of them, effectively you're getting a 0 point versus, actually having a concrete estimate about what it comes from, and then comparing your risk of those events to, anything else that comes along the way. Is there any way that people can essentially apply the actual vaccines are meant to elicit an immune response? And so, for example, you can actually tell, presumably you can get an antibody test after your vaccine to understand whether or not you've actually had an immune response. And that seems like something that would be extremely useful, especially when we look at the, I believe it's the Delta type variant that has popped up in the UK. The last data that I saw was something like, of the 60 people in the UK who have died of the Delta variant. I might be getting these numbers completely wrong. I'm just trying to remember them off the top of my head. But I think there's 60 people of the 15 who died, they had been fully vaccinated. And the question there is, well, did they have any immune response? Previously, did they have an antibody test that indicate that the vaccine gave them an immune response? Because there are plenty of people where if you don't have an immune response, well, then it didn't do its job. That whole efficacy thing that we've been trying to monitor. But given that we know that there's a biological mechanism that causes this reaction to the vaccine, is there any way that we can essentially try to guess what these long-term effects are better than just saying we have to collect data and find out? Because obviously, even if it's just purely, inductive speculation that we know that these types of immune responses happen for this variety of vaccine, and therefore we know that these might be the types of things to look for.
Yeah, so with vaccines, there are certain outcomes that we typically always look for, irrespective of what vaccine there is, because there's been sort of past situations where we see those things. So one is anaphylaxis, which is an allergic reaction immediately after you get the vaccine, for which there's a very, very small risk from COVID. So which means that you should hang around in the vaccination site for half an hour just in case it happens, so you have medical personnel to take care of you. Another one example is Guillain-Barré syndrome, which wherever there's a new vaccine, we always test for that. For childhood vaccines, we usually look at febrile seizures as one outcome from vaccines. But then there are other things that can come up that are unexpected. So when it comes to what kind of adverse reaction to look at, there are some things sort of a standard thing that we look at, but then there are other things that could be a complete surprise.
Cool. Yeah.
But it's hard to predict what might be the adverse reactions without looking at long-term data. So I think it's hard to predict, because this vaccine has this mechanism, and therefore and we look at antibodies or something to see what happens in the body for the few weeks later, and therefore we suspect this type of adverse reaction. I think that's very difficult to do. We don't know enough about medicine to be able to do that without actually looking at long-term data.
Martin, thank you so much for your time today. I've really enjoyed our conversation and hearing about the sort of statistical mindset that goes behind some of the work that you do for essentially surveillance. And I think it is really interesting because you're answering multiple very difficult scientific questions. You're trying to use data where you have it, and you're trying to use just sound logic where you have it as well. So I do appreciate that. I also appreciate very much your scientific integrity in everything that you've been doing. And I really look forward to having you back sometime. If you enjoyed this, we can talk. We can pick up another topic and continue the conversation. But Martin, I really appreciate your time today.
Thank you, Glenn. One of the things that's fun with being a scientist is to talk about science with other scientists. And I really enjoy this. And I'll be happy to be back some other time. So thank you so much, Glenn.
Yeah. Actually, I have to say, because I obviously watched quite a few of your interviews, and this thing is like, I wonder if he's actually gotten to have a conversation with a statistician yet. And so I've appreciated that. And that's one of the places where I think I'm wanting these conversations to go, where I think a lot of statisticians are eager to hear from scientists, very specifically asking data-driven and scientific questions and statistical questions that they might not get from other sources. So, you can always have a very good scientist and two scientists having a conversation. But, statisticians, whenever we read the news or read a journal article or something like that, we tend to think like, oh, well, I would actually have asked this question, because there's cool stuff that I'd like to clarify. And I'm hoping that this can be sort of a hub for statisticians asking very data and sciencey questions.
Yeah, you're the first statistician that has interviewed me, so I appreciate that. And it was nice to be able to go into a little bit more about the depth of the statistics and be able to actually mention statistical terms and get a more thorough discussion that way. So I like that.
Cool. Yeah. Well, actually, in the future, I very soon will have a sketch pad so we can actually draw out ideas. And maybe that will help with some of our point process conversations and things like that. Because because I know that maybe using some of these terms, it's very visual for me because obviously, I've seen plenty of spatial-temporal modeling. I've seen plenty of the Gaussian process and latent process modeling that goes into these things. So maybe it'll be easier to help people hop on board and understand these things better if I can be there sketching out ideas as you're talking about them.
Yeah, a little sketchbook is good for discussing science and statistics. So
cool. Well, Martin, thanks again for your time. I appreciate it.
Thank you, Glenn. Great pleasure.
Hey guys, it's Glenn. Thanks for your time today. I hope you liked today's episode. If you did, please consider smashing that like button. It's the single, simplest, fastest way to make sure that YouTube shows this video to more people. If you really want to go crazy, consider subscribing or going to our website and joining the mail list. If you want to go totally crazy beyond that, forward this to a friend or colleague who you think might enjoy this too. We're a small channel and every bit helps. Our next episode will be coming out next week, so in the meantime, feel free to look around the channel and see other videos that might be of interest. As a quick disclaimer, the views expressed in the show do not represent anything other than the people saying those words, views, etc. like that. It doesn't mean anything about their employers or their employers' views or some thing about their employers or their neighbor's cat or anyone else not saying the words. And in fact, given that people tend to change their views when they're thoughtful enough, it might not even represent the views of the speaker by the time you're hearing the episode. So definitely come back and see if they've changed their views at a later date. They also don't represent the views of our sponsors. Thank you to our sponsors. You can check them out on our website.